In this video, we will prove the maximum modulus principle. In this lesson, we will prove the maximum modulus principle, which is an important result involving maximum values of the moduli of analytic functions. In our proof of the maximum modulus principle, we will need to use Gauss's mean value theorem, which I'll state now. If f is an analytic function in a simply connected domain D, that contains the circle we'll call it capital CR, which is the circle containing point Z such that Z minus Z0 and absolute value equals R. So this would be the circle centered at Z0 with radius capital R. Then we have that f of Z0 can be written as 1 over 2 pi times the integral from 0 to 2 pi of f of Z0 plus capital R times e to the I theta d theta. And though I'm not going to give the proof follows from using the parameterization of the circle C sub R in exponential form. So if we write C sub R as in parameterized form Z0 plus capital R e to the I theta for theta between 0 and 2 pi, we just use this parameterization and Cauchy's integral formula, then we can establish Gauss's mean value theorem formula. So we'll use this in our proof of the next statement, the maximum modulus principle. So the maximum modulus principle states that if we let f be analytic and non-constant, in a domain D, then the modulus of f of z has no maximum value in D. So since D is a domain, it is an open connected set. The absolute value of f of z attains no maximum value. So the proof of the maximum modulus principle is a proof by contradiction. So we're going to assume that f has a maximum value in the domain D and get a contradiction. So let's begin the proof. For a contradiction, suppose that f of z in absolute value is less than or equal to f of z, the absolute value of f of z0 for some z0 in the domain D. Now I want to define a circle C sub R that's contained in D. So you let C sub R be the circle absolute value of z minus z0 equals R, and we'll choose R so that this circle is contained in D. Then for any value little r that is between 0 and capital R by Gauss's mean value theorem, we have that the absolute value of f of z0 will equal the absolute value of 1 over 2 pi, the integral from 0 to 2 pi, f of z0 plus little r e to the I theta d theta. And by moving the absolute values inside the integral, we have that this expression is less than or equal to 1 over 2 pi times the integral from 0 to 2 pi of the absolute value of f of z0 plus r times e to the I theta d theta. But we're assuming that f in absolute value is less than or equal to f of z0, so the integrand is going to be less than f of z0. So this expression will be less than or equal to 1 over 2 pi, integral from 0 to 2 pi, absolute value of f of z0 d theta, and I can pull the f of z0 and absolute value outside as a constant, and we get the integral from 0 to 2 pi d theta, which equals 2 pi, and so the 2 pi's cancel, and that's just equals the absolute value of f of z0. So we started the chain of inequalities with the absolute value of f of z0 and ended with the same expression, absolute value of f of z0. Therefore, the intermediate expressions must all equal f of z0 in absolute value. So in particular, the absolute value of f of z0 will be equal to 1 over 2 pi times the integral from 0 to 2 pi of absolute value of f of z0 plus r e to the I theta d theta. Remember, r is any value between 0 and capital R. Then I can rewrite f of z0 as an integral, and we can write the following expression. We have that 1 over 2 pi times the integral from 0 to 2 pi of the absolute value of f of z0. So if this was just the integrand, this whole integrand will just equal absolute value of f of z0 minus the integrand from the last equation, so the absolute value of f of z0 plus r e to the I theta d theta. And so from this last equation, when we integrate this, we get 0. Now notice that the integrand in this last expression is a non-negative function, since we're assuming that the absolute value of f of z0 is greater than or equal to any other value of the absolute value of f. So since the integrand is non-negative, and this is a continuous function on the real interval theta between 0 and 2 pi, the only way we can have this integral of this non-negative function equal to 0 is if the integrand is identically equal to 0. So first, note that the absolute value of f of z0 minus the absolute value of f of z0 plus little r e to the I theta. This expression will always be greater than or equal to 0, since the absolute value of f of z0 is the maximum of f in absolute value. And this integrand is a continuous function of theta. On the interval from theta equals 0 to theta equals 2 pi. And since the value of the integral is 0, the integrand must be identically equal to 0. So we have that the absolute value of f of z0 plus r e to the I theta equals absolute value of f of z0 for any little r between 0 and capital R, and for theta between 0 and 2 pi. So we see that the absolute value of f is constant on the disk centered at z0 with radius capital R. But we've already showed that if the absolute value of a function is constant in a disk, then the function must be constant in the disk as well. Since the absolute value of f of z is constant, in the disk, absolute value of z minus z0 less than or equal to capital R, we have proven previously that this implies that f must be constant. On this disk as well. So if the absolute value of a function is constant on a domain, then the function itself must be constant on that domain. So therefore, f of z equals f of z0 for all z in the disk, absolute value of z minus z0 less than or equal to capital R. So we showed that if f attains a maximum on a disk, then f is constant on that disk. Now we will extend this to show that f must be constant on the whole domain D. So I'm going to let W be an arbitrary point in D. And we're going to show that f of W must also equal f of z0. And so the function is constant on the whole domain D, which would be a contradiction. Also, let C be a contour contained in D that joins z0 to this arbitrary point W. Further, let's let lowercase d be the shortest distance from this contour C to the boundary of the domain D. Now, in the case where D is the entire plane, we could choose any positive value for D. So if D equals complex plane, and choose any positive value for D. let's draw a picture of the situation. So we have our domain D, and we have Z0 somewhere in the domain, and we have another arbitrary point W in the domain, and we have a contour. It could be a polygonal path, it could be a straight line, but we have a contour C which joins Z0 and W. Now D is the shortest distance from the contour C to the boundary of D, so we're going to cover this contour by disks with radius D. So we're going to have open disks centered at points along C that overlap, and so there's going to be points along the contour C. So we have Z1 and then Z0 and then Z1, and we're going to use disk of the same radius, and the radius is going to be D. So all of these open disks are going to be contained in D, and we're going to continue until we cover the whole contour C with these disks. So we have Z sub n minus 1, and then we'll end with W, which will be our Zn. So we're going to cover the contour C with these disks, and by extending the argument that we just made, we'll show that f must be constant on each one of these disks, and as we go along, that'll show that f of W must equal f of Z0, and therefore the function is constant on the whole domain. So the idea is we can cover the contour C with a chain of disks we're going to call these disks D0, D1, all the way up to Dn, each with radius lowercase d, so that way they're all contained in the domain D. And they're going to be centered at points along C, so they're centered at points Z0, Z1, Z2, all the way out to Zn, which will be W, which are all on the contour C. But we want these points to be less than distance D away from each other, so that the disk at Z1 will contain the center of the previous disk, Z0, and so on along the line. So the absolute value of zk plus 1 minus zk will be less than little d. So we define more explicitly the disk dk will be the set of all z, so the absolute value of z minus zk is less than d for k equals 0, 1, 2, up to n. And so we see that each disk contains the center of the next disk. We have these disks. D0 will be the first disk centered at Z0. D1 will be centered at Z1, and so on down to D sub n minus 1 and D sub n. And we see that in the case of Z1, Z1 will lie inside D0. So Z1 lies inside D0, And thus, by the previous argument, the absolute value of f of z also reaches its maximum value at z1. So using the same argument as above, we can conclude that f of z1 must equal f of z0 for all z in D1. So using the same argument as above, we conclude that f is constant on D1, and therefore f of z equals f of z1, which equals f of z0 for all z in D1. And then we proceed down the line along this chain of disks So proceeding inductively, we get that f of z equals f of z sub k plus 1, which equals f of z sub k for all z in the disk d sub k plus 1. And k is between 0 and less than n minus 1. So putting this all together, we can conclude that f of w, which was f of z sub n, would also equal f of z0. And since w was an arbitrary point in the domain D, we see that f is constant in the domain D. But this is a contradiction since we assumed that f was non-constant. So this finishes the proof of the maximum modulus principle. So we have proven that if f is an analytic and non-constant function in a domain D, then the absolute value of f of z does not attain a maximum value inside the domain D. We can actually restate this maximum modulus principle in terms of closed regions in the following way. Let's let f be analytic and non-constant in the bounded domain D, if f is continuous on the closed region consisting of D and its boundary, and all of its boundary points, which I'll write as a set, capital B. So if we have a continuous analytic function on a closed bounded region, then we know that f attains its maximum. But by the statement of the maximum modulus principle that we had earlier, the maximum cannot occur on the interior of this closed bounded region. So we can conclude that the absolute value of f of z assumes its maximum somewhere on the boundary. So then the absolute value of f of z assumes its maximum value somewhere on the boundary B. So again, the difference is that on the closed region consisting of D and its boundary, f in absolute value attains its maximum, and since it can't attain it in the interior, the maximum must occur somewhere on the boundary B.